Does physics serve as our best guide to metaphysics? What fundamental metaphysics is best motivated by quantum mechanics? And what's the deal between the age-old beef between philosophers and physicists? Here today to answer all these questions and more is none other than my friend David Albert himself, a renowned philosopher and physicist widely recognized for his contributions to the philosophy of quantum mechanics and the foundations of physics.
When I'm writing a paper is that when I'm done, there are less than 2 equations in it, I send it to a philosophy journal. If there are more than 2 equations in it, I send it to a physics journal.
In our stimulating conversation, we talked about his controversial proposal.
This was not a popular topic to work on in physics departments.
And the truth about quantum mechanics, Einstein's affection for Ernst Mach, and who would win in a fight between a physicist and a philosopher. Let's go.
David, welcome to wet, cold, frigid San Diego.
Glad to be here.
We've been talking, we met in person a couple months ago, courtesy of Robinson Earhart, another YouTuber, philosopher of science up at Stanford, who recorded an episode with me 5-6 months ago. Robinson is still waiting for that to come out. But he's had you on 4 or 5 times. And every time is just delightful. And we met in a very famous location, renowned for its pastry and its tourism, the Hungarian pastry shop in the Upper West Side of New York in November when I was there visiting your colleague, Brian Green. Mm-hmm. And you graciously agreed to not only come and do the podcast, but come to San Diego and give a colloquium. So today you're giving a colloquium. We'll get into that in just a bit. The first thing I always love to do on this podcast, as I mentioned, is do what you're never supposed to do, which is to judge a book by its cover. Now, we don't have your book. I have it on Kindle, so can't really show it up to the camera. But if you can remember it and describe your book, it came out, I think, in 2023 September.
Right.
So just before we met, describe your newest book and what caused you to write it. As I understand, it's sort of like an epilogue to your very well-known book, Physics from Experience?
Quantum Mechanics from Experience, right.
Yeah.
Yes, it's sort of an epilogue to that book. Basically, that book was meant to be a sustained argument that the possibility of looking to quantum mechanics for an account of what the world was really literally like was something we could do, that we had spent the better part of a century under the influence, especially of figures like Niels Bohr, thinking that the aspiration for a sort of realistic account of what the world looked like was more than one could ask for from quantum mechanics, that the behaviors of subatomic particles were simply not going to lend themselves to that kind of a description, that the best we could hope for is to discover algorithms for calculating the probabilities of outcomes of measurements, and the idea of going beyond that to a sort of realistic, in the philosophical sense, picture of what the world is doing, of what it is that accounts for the way these experiments come out, was too much to ask. And this book was meant to familiarize its readers with all sorts of developments that had occurred over the 30 or so years before that book was written, but which had not gotten the kind of broad exposure that they deserved. Mm-hmm. All sorts of ideas that showed that these claims of Bohr's were simply wrong, premature, jumping to very grand conclusions without sufficient reason. In particular, the big impediment to a realistic understanding of the micro world was this so-called measurement problem that comes up in quantum mechanics. Bohr was adamant that the measurement problem not only wasn't a problem that could be solved, but wasn't the kind of problem that you ought to approach with the aspiration to solve it. That this was a piece of naivete, that what the measurement problem really represented was an encounter with the limits of the capacity of human reason to penetrate the inner workings of the world. And like I say, this book of mine, Quantum Mechanics and Experience, was basically aimed at resisting that whole view. Not the crucial discoveries here weren't mine. They were discoveries of other people like David Bohm, or the Italian physicists Ghirardi, Ramini, and Weber, or Hugh Everett, or people like that, but whose attempts at being realistic about quantum mechanics hadn't gotten the kind of traction, certainly in the physics community, also in the philosophy community, that they deserved. So this book was aimed at introducing people to that, as putting the project of a realistic account of the world, of the subatomic world, back on the table, as putting back on the table the idea that physics could serve as our best guide to metaphysics. And the book was meant to argue for that. It wasn't so specific about, okay, now that this project of realism is back on the table, what is the correct realistic description of the behaviors of subatomic particles of the kind that quantum mechanics treats? This most recent book of mine, which is called A Guess at the Riddle, is just what it says. An attempt, I mean, there are lots of different proposals on the table now. You know, a brief thumbnail sketch is 30 years ago, a bunch of people, including me, were arguing that the project of using physics as a guide to metaphysics should now be back on the table. Now that we had seen that the measurement problem was not, as Bohr thought, an encounter with the limits of human reason, but a scientific problem like other scientific problems, a scientific problem that we should entertain every hope of solving in the way we solve other scientific problems. Now that that had been achieved, the ground was reopened to speculation about what kind of world it is that quantum mechanics was describing to us. That's still a very open question. That's still a much debated question. And this most recent book of mine, called A Guess at the Riddle, is an attempt to contribute my own 2 cents to that. It's a particular picture of the sort of metaphysical structure of the world that I think goes along well with quantum mechanics. But it's not, the first book that I wrote 30 years ago was meant to be very conclusive. These arguments of Bohr that a realistic picture of the world was simply not going to be available were wrong. And I was determined to be very forceful about insisting that they were wrong. And other people were in similar positions at the time. And that's an argument that it feels like was pretty decisively concluded for people who were really interested in these foundational issues. And nowadays, you just don't find many fans, many advocates of the sort of anti-realistic Copenhagen type of position around anymore. But like I say, that opened up a whole new set of questions. Okay, if a realistic understanding of this theory is not blocked any longer by the measurement problem, what are the most plausible ideas around about what that metaphysical structure would be? Like I say, this new book of mine is an attempt to contribute my own 2 cents to that ongoing debate now.
On the cover, there's this kind of remarkably beautiful but somewhat mysterious tapestry. I wonder if you could describe it, or what we're looking at on the cover. And the subtitle is also Essays on Physical Underpinnings of Quantum Mechanics, which is, I guess this book to me has a more tentative sort of approach, because it has the word guess in it, and you're saying it's essentially less forcedelic kind of input. So anyway, describe the cover, this picture that we're looking at.
So the cover is this sort of psychedelic, floral, vegetative fantasy, and this is supposed to just evoke, or it evoked for me, this sort of richness of detail that the wave function of the world is supposed to describe. And this book, the guess that I'm making in this book is that the right way to understand quantum mechanics is to treat the wave function not as a compendium of probabilities or something like that, not as an abstract description of what's going on, but as a concrete physical object, indeed as the concrete physical object that is the world, that has every little curlicue of the actual history of the world in it. And the painting was something that I thought evoked that kind of richness. It also happens to be a painting. It also happens to be the case that the painter was my wife.
I was going to say,
and that was another nice thing about being able to use
keep
this
it
painting.
in the family. Speaking of family, a lot of our PhD listeners out there know that you have a very tight relationship when you're a PhD student with your advisor. In some ways, it's closer than our spouses or friends. It's for some of my colleagues, at least I'm told. Your advisor was officially Nicolas Curie.
That's right.
And he, if I'm not mistaken, has sort of a claim to fame. One of his many claims to fame was that he convened the second Shelter Island Conference in 1983, which would have been right after you graduated.
That's right. That's right.
Were you there?
I wasn't there.
Oh,
no.
God. Oh,
No.
what a horrible
mishap.
Yeah. Wow. But you must have had, kind of trafficked in those same circles. I understand.
Well,
Feynman
there was.
there.
That's a funny story.
Yeah.
It may be a story worth telling.
Yeah, please do.
Nicolas Curie was a lovely man. I was interested when I was in graduate school in working on issues about the foundations of quantum mechanics. In those days, this is the late 70s, early 80s, this was not a popular topic to work on in physics departments. There was amazing hostility towards this. I was interested in these questions. I didn't know who to talk to about it. There wasn't anybody in my PhD. There weren't any faculty members in my PhD program who were interested in those kinds of questions. Not only none who were interested, but none who weren't actively hostile to wondering about those sorts of questions. So I ended up just writing a letter about stuff I was thinking about to Yakir Aharonov of the Aharonov-Bohm effect.
We'll get to him.
Who was very nice. This was in the days of snail mail. I wrote to him. I told him some stuff I was thinking about. He was very kind to me, wrote back. We started doing some research together by snail mail.
I'm sorry to interrupt, but why him instead of one of the other?
He was the only physicist I knew of at the time who was famously and actively and deeply and, sensibly interested in these foundational questions.
Wow.
I just didn't know of anybody else working in physics at that time who had an active public interest in these kinds of subjects. I mean, the exception maybe was John Bell.
Bell, yeah. He died in the 80s.
Oh, yeah, he died. No, he died much later. Yeah. But anyway, I ended up, it's a good question why I didn't write to Bell.
Yeah.
I ended up writing to Aharonov.
Yeah.
He was very nice. He was very helpful. We corresponded by snail mail, published a couple of papers in physics journals before we ever met. And I was very happy about this work and very interested in it. And I told the people at Rockefeller, which is where I was a graduate student, that this is what I wanted to do a thesis about. And the response to that was not a happy one. The day after I made this announcement, I got a notice from the dean's office at Rockefeller saying that I needed to show up for a meeting at the dean's office.
Never a good sign.
With people in my department because there was consideration. It was under consideration to ask me to leave the PhD program.
Wow.
When I got to that meeting, I was sort of presented with an ultimatum. They said, look, first of all, you're not doing a thesis about these issues that you're working on Aharonov with.
Passion project.
We're not going to do that, and we're not going to have our students doing that. Second, we have a problem. We have a calculation-heavy problem in phi to the 4 quantum field theory, which people used to fool around with in those days. We have a very calculation-heavy problem, which we think would be good for your character. Your choice is either to leave the program or to work on this problem. This was a problem that Professor Curie, who was a very nice man, a generous man, a kind man. Apparently, there was a discussion among the faculty, are we going to kick this guy out of the program? And Curie apparently spoke up and said, I can give him a problem, and that'll be acceptable to everyone. It'll be good for his character, and it's not anything in the neighborhood of foundations and so on and so forth. This was a problem. I won't go into it. It was a very technical issue about Borel resumming the individual terms in the perturbation expansion of this fight of the four field theory. I was told, either you do this problem or you leave. I got in touch with Aronov. We talked about it for a while. Aronov said, look, my advice is put your head down for a year, do the problem, get through,
graduate.
And I give you my word, the minute you've got your PhD, I will give you a job in Tel Aviv, and we can work on this stuff together, and you can work on whatever you want to. And that sounded like good advice to me, so I did it. But so my relation with Professor Curie was basically just that he was a good Samaritan. We weren't intellectually very close. He wasn't interested in these kinds of things that I was interested in. So I sort of put my head down, got that done, got my PhD, and went to Tel Aviv to work with Aronov. So really, my apprenticeship in thinking about physics and about foundations of physics was much, much more with Aharonov
So you weren't there
than it was with Curie. Curie's main contribution to my career was being a very nice man.
Yeah.
Somebody who took pity on a student who seemed earnest and not stupid and was getting kicked out of the department, and he sort of saved my neck. But there wasn't much of a sort of intellectual kindredness
internship
there.
as typical, right? So speaking of the thesis, I'm told this may be apocryphal squared, but allegedly in your thesis you were still sort of perturbed by the fact that you weren't allowed to pursue your dreams.
That's
and you
right.
quoted my favorite physicist of all time, Galileo.
Right.
Eppur
That's right.
se muove,
That's right.
and yet it moves. Why would
Right.
you do such a thing? What was the meaning behind that,
because
David?
I'm a self-destructive, crazy person. I mean, I put this quote, as the epigraph of my thesis when I submitted it.
For those that don't know, apocryphally they say that.
Right. They say that this is what Galileo said. Galileo, upon being released by the Vatican Inquisition, after having renounced his view that the Earth moves under threat of torture, he was given a tour, I understand, of the Vatican torture
Implements,
chambers,
right.
And he renounced his belief that the Earth moves. And supposedly, on being released by the Inquisition, he stamped his foot on the ground and says, "It moves anyway." In Italian, "Eppur si muove." It still moves, as if to say, "I don't care what you forced me to say. This is the truth." And I guess I felt similarly.
Really?
I felt in
in
a sort of analogous position, not nearly as extreme, of course, but I was forced to renounce this work in Foundations of Quantum Mechanics in order to get a PhD.
I always say it's always perilous to compare yourself to either
Yes.
Bruno or
Yes.
Galileo.
Yes.
And they'd be taken seriously.
But that's what that was about. That caused a bit further ruffling. First of all, it took people a couple of days to figure out what the Italian quote meant.
Yeah, with pre-internet.
And at that time, I'd kept my part of the bargain. They gave me my PhD.
That's good.
Everything came out okay.
So speaking of my hero, the great El Maestro Galileo, it is not a apocryphal story that in Sidereus Nuncius, or after Sidereus Nuncius, and it's his groundbreaking work when he illustrated and had very tentative ideas about Copernicanism, but that wasn't his main goal. He said, because of the observations that I have made and presented in this book, we are therefore liberated from the wordy arguments of the philosopher. You're a philosopher. Do you take umbrage at this? And can you say anything about the beef, the eternal East Coast, West Coast, like rap battles between physicists, pure physicist, hardcore physicist, and philosophers? Does physics need philosophy? Did it ever need philosophy? What do you make of these rap-like battles?
I mean, when the philosophy that Galileo was liberating the world from was Aristotle, okay? Aristotle, had very different ideas about physics than we do now, and they were ideas that required a decisive rejection, and it was enormously important that the fulcrum of this rejection, that the engine of this rejection was empirical. Observation. And this changed our whole approach to figuring out what's going on in the world.
Yeah. Plato, we have a problem. I repeat, I just checked my analytics, and it seems that only about 50% of you are subscribed to my YouTube channel or following the podcast and audio channels. This must be a mistake, because according to my philosophy, you are really enjoying this content that I'm putting out. So please, unless other complications arise, please hit the subscribe button or follow the podcast on your favorite streaming platform of choice. And don't forget to leave a review. Even the ones that are critical, I treat those very seriously as well. Now back to the episode.
Good. But what Galileo loosed on the world was something, in the figures of people like Newton and Leibniz and so on and so forth. It goes without saying that these people felt that they were very, very close to the philosophy of their time, right? Not an Aristotelian philosophy. And they felt that they were raising philosophical sorts of questions. And of course, not that names mean anything, but in those days, these people were called natural philosophers. That's what they describe themselves as doing for a living. There have been, I would say, at moments when there is one or another sort of crisis in physics, philosophical sorts of reflections invariably become very important. I think it's now a commonplace that, this is not something that people debate so much, that Einstein wouldn't have come up with special relativity if not for Mach, okay? And if not for, in particular, the Machian analysis of time, the Machian insistence that all you mean by time, what you mean by time and all you mean by time is what it says on a good clock, okay? That this shouldn't be regarded as an instrument for measuring something more abstract or occult or invisible. That's what you mean by time. And what Newtonian mechanics asserts is a set of claims about correlations between the positions of particles that you're interested in and the positions of the hands on a good clock. And it's very well known as a historical matter that Einstein he didn't just read Mach, he inhaled him, he ingested him. And by Einstein's own testimony, this is what allowed him to think in a way that was going to give rise to the special theory of relativity. And of course, Mach was a big influence also on the formulation of the general theory of relativity. Right. Einstein's original motivations had a lot to do with sort of justifying Mach's principle of the origin of inertia. Now, that turns out not to be what general relativity does, right, but it's uncontroversially a very big motivation of his in the formulation of general relativity in the first place. Good. So there's always been this dialogue across the boundary between physics and philosophy that I think has nourished both of them. By the way, I wouldn't say that the only question is what can philosophy do for physics. There's a question of what physics can do for philosophy. That's right. Okay. This has been very much of a two-way thing. Recently, I think it's gotten even more productive, I think, in the following sense, especially because of problems in the foundations of quantum mechanics, and to a slightly lesser extent, but to a significant extent as well, in discussions of the arrow of time. Problems have come up in the physics which are of a kind that it requires a certain degree of philosophical talent and philosophical sophistication to get straight about even what the questions are, what kinds of questions would need to be answered in order to give us a reasonable theory of what's going on, what would count as a satisfactory answer to those sorts of questions. In quantum mechanics in particular, this has been very important over the past century. And the business of recognizing that there is such a thing as a measurement problem in quantum mechanics. Ironically, if you were to ask, what's the important achievement of people, and I don't know what you even mean by philosopher. I don't know what I am. My PhD was in physics. I was a professor in physics departments for several years before I started being a professor in philosophy departments. I publish, my rule when I'm writing a paper is that when I'm done, there are less than 2 equations in it, I send it to a philosophy journal. If there are more than 2 equations in it, I send it to a physics journal. So I don't know what I am, okay? But there have been, and this is typical of, I think, what's been productive lately. There are these, the chief achievement of philosophers over the last 30 years or so about foundations of quantum mechanics has been to argue that this measurement problem is not a philosophical problem, it's a scientific problem. So ironically, what philosophers have contributed to our understanding of this field has been principally by insisting, no, this is a physical problem. It needs to be solved by modifications of the physical theory that lead to different empirical predictions, and so on and so forth. So the contribution of philosophy has been to say, this is not philosophy. This is physics we're talking about here. And because of this, the interlinking of people employed in physics departments and people employed in philosophy departments who are interested in this tangle of issues has become much closer and much more fertile. And if you go to conferences now on the foundations of quantum mechanics, some of the speakers will be from physics departments, some of the speakers will be from philosophy departments, and it won't in general be easy to tell by listening to their talk which department they happen to be employed in.
Right.
So the meshing of these two has become much deeper, much more intimate recently than it was before. But even before, as I say, what was Leibniz? I don't know. Not that many people would call him a physicist. He was a mathematician. He was a philosopher. Certainly, he was very intimately involved in working out and debating with Newton about what the actual structure and meaning of Newtonian mechanics was. This has been a debate at the fundamental level which has been, I think, profoundly productive for both fields for a long time. So it's right that there's a sense in which Galileo liberated science from philosophy. I would say he liberated science from a philosophy that had a bad understanding of physics.
And pure thought. Of course, he trafficked in thought experiments, as did Einstein, and the importance of those has somewhat waned as physics has matured. But I want to ask a question that I ask a lot of my theoretical physics colleagues, including people like Lenny Susskind, who's been on the podcast, I know, obviously you know, and that is what I call the experimental minimum. Typically, I'll ask a theorist, what are the minimum things about experimental cosmology, astrophysics, particle physics? What are the fundamental bare minimum that your PhD student in theoretical physics should know about experiment? I'm not going to ask you that. I'm going to ask you a different question. What do you think physicists in general, theoretical physicists, experimental physicists, what's the theoretical minimum that they should know about philosophy, philosophy of science, philosophy of physics, interpretations of quantum mechanics, etc.?
I mean, to tell you the truth, I'm not sure how to answer that question. It isn't, I think an enormous amount of enormously productive physics can go on without attending to these foundational questions. And indeed, in certain circumstances, I think you can make the argument that attending to foundational and philosophical questions would have been an impediment to the progress of physics. It would have slowed it down. It would have gotten people stuck. Okay? I'm a big believer in division of labor. Okay? There are people who are interested in, what happened over the course of most of the 20th century, from like the mid 1920s to the mid 70s or 80s, was that there was this unbelievable progress in the development and application of quantum mechanics and quantum field theory and so on and so forth. The concrete achievements of this development were unbelievable. Okay, chemistry vanished as a separate subject. Okay, it was clearly just a special case of quantum mechanics, and our understanding of the structure of matter at increasingly microscopic scales with the advent of quantum field theory and so on was incredible. All of this could go on amazingly in the context of a basic theoretical, conceptual structure that made no sense, okay? That had a logical contradiction at the bottom of it in the measurement problem. It's amazing that this could happen, but it could, and it did. And if everybody who was trying to develop quantum field theory and so on had been slowed down by these worries about the foundations of quantum mechanics, that probably wouldn't have been a good thing for physics. The only thing that's silly is to be hostile to people who do happen to be interested in these foundational questions and are trying to press them forward. There's no reason to be scared of these people. There's no reason to be hostile to these people, as people very much were, okay? Even a figure, of the stature of Einstein, as everybody knows, was towards the end of his life a marginalized figure. And this was principally because of his worries about the foundations of quantum mechanics.
And the search for unification.
Right. And that, although the quest for unification didn't turn out to be so out of step, we've got we've got things very much along those lines now. I think it was mostly because of his worries about the foundations of quantum mechanics. And moreover, looking back on that period now, the ironic thing is Einstein's worries were right on the nose.
Absolutely.
They
and
were
Bohr,
absolutely correct.
People tease Einstein because they say he didn't do anything original after 1917, which is not altogether, accurate. But what did Bohr do? There are a couple.
So Einstein,
sure, yeah.
Einstein.
I'm not throwing shade at Bohr, by the way.
Right on the nose about this. So that, I think, was very unfortunate that there was this kind of hostility. I think the history of that is very complicated, involved with all kinds of other developments in the 20th century. There's a very nice first attempt at writing a history like this. A book that came out a couple of years ago called What is Real by Adam Becker.
Yeah, he was on the podcast with my late colleague, Andy Friedman.
I see. And I think he did I think there's a lot more to be said about this. I think it's just a first attempt, but I think there's a pretty good attempt at doing that. Yeah, what was crazy and what was unfortunate and what was interesting is that thinking about the foundational stuff became the target of lots and lots of hostility. So my attitude is, no, I don't have any kind of a problem with physicists, both experimentalists and theorists, who say, you know what, I'm interested in applying this formalism. I'm making really good progress. Both,
the merman shut up and calculate.
Yeah, that's
you don't
right.
have a problem with them.
I what I do is I shut up and calculate. I get lots of results from this. They're really important. They're really good. I think that's great. Okay. There are certain people who will be inclined and whose talent lies in the direction of shutting up and calculating, and there will be other people who will be inclined and whose talent and inclination lies in the direction of focusing on the foundational questions. I think a lot of progress has been made in both. I mean, I think, even technological progress. I mean, the whole recent business of quantum computation is a pretty direct spin-off of people trying to figure out foundational issues in quantum mechanics. I don't know what the philosophical minimum is. I don't know that you need that. If people are doing good, productive work while ignoring other kinds of good, productive work, that's fine with me.
Okay, great. So I had on your fellow denizen of the New York Isle, the Isle of the Manhattoes, as Herman Melville called it in Moby Dick, David Chalmers. And he was on, and we discussed consciousness and the brain, and here's Brian's brain over there, life-sized for you. Probably it's probably way too big for me. But one of the things I said to him, I said, David, there's an elephant mastodon in the room, and that's akin to if I were to be interviewing your fellow countrymen from Australia, AC/DC, and I didn't ask them to play, Back in Black. I mean, I'm not doing a service to my audience. Okay, so I said, David, for you, that's the description of the hard problem of consciousness. Okay, that's what you're known for, etc. One of the many things you're known for is the past hypothesis. And I want to pivot to that and why that has, in some circles, become controversial. In some circles. And I would say it's controversial in that it is supported by folks like many-time guests on the show, Roger Penrose and others, as pointing out a fatal flaw in the dominant paradigm of my field, which is cosmology, inflationary cosmology, and the stipulation that there's somehow the universe started at a very low entropy state. Can you explain what this problem is connected to your 2000 book, Chance?
Time and Chance.
Yeah. Book, right. What is the past hypothesis? First, that's your AC/DC moment. First define it, and then why is it interesting, important, and what are the implications for card-carrying cosmologists like me? And
so I'm the one who coined this term, the past hypothesis, but I think this is an idea that really goes back to Boltzmann. There's
also known for his brain.
There's a very straightforwardly describable puzzle, given the structure of our fundamental physical laws, about the direction of time that comes up as follows. Our basic dynamical laws all have this, every proposal for the fundamental dynamical laws of the world from Newton through string theory, okay? Although these proposals have differed in enormous ways about the structure of space and time, about the question of determinism, all kinds of stuff, astonishingly, something that all of them have in common is that they have a property that physicists call time reversal symmetry. Okay, that is, all of them have this property that if a certain process is possible in accord with the physical laws, then the same process going exactly backwards is also possible in accord with the physical laws. And this immediately presents a problem because for example, one of the implications of this time reversal symmetry is that if I'm shown a film of a certain physical process, which is in accord with the fundamental physical laws.
Pendulum swinging back.
Right. For example, I'm shown the same piece of film backwards. Okay. That will necessarily depict another process which is also in accord with the physical laws, so that if I were shown a film of a physical process, like a pendulum swinging, say, and asked to guess whether I'm being shown the film forwards or backwards. I couldn't on the basis of any knowledge of the basic dynamical laws. Okay, but the minute you start thinking about processes that you witness in everyday life, okay, people walking down the street, people aging in time-lapsed photography, soup cooling, smoke spreading in a room, so on and so forth. This is obviously crazy. Of course we can tell whether we're watching films of processes like that, forwards or backwards. So what's going on? The world is filled, the universe is filled with all sorts of processes that seem to happen in one temporal direction but not in the other. And if you put that beside the fact that the fundamental dynamical laws don't contain any distinction between going forwards in time and going backwards in time, there's a very obvious puzzle, okay? And this puzzle is referred to as the problem of the direction of time. And the person who undoubtedly thought the most deeply about this problem was Boltzmann. Yeah. Boltzmann didn't put it exactly this way. The first person who I think put it in a really clear way was Feynman, in a certain portion of the Feynman lectures, where he said, look, in order to explain the fact that coffee tends to cool in a cool room and not to get hotter, that smoke tends to spread out from a cigarette and not collect back into the cigarette, and so on and so forth, we're going to need, in addition to the time reversal symmetric equations of motion, some kind of restriction on initial conditions, some kind of restriction on the initial conditions.
An instantiation of a...
That's right. That's right. And it's only going to be with the addition of such a restriction, okay, that we're going to be able to derive that smoke almost never collects into a cigarette,
coffee
that coffee almost always cools, so on and so forth. And this applies to more abstract things too. It's not just thermodynamic processes. For example, we have a very different epistemic relation to the past than we do to the future. There are lots of things we know about the past. We know with certainty. We know with great accuracy. We don't know things about the future in the same way. Why should this be true if the fundamental laws of physics don't make any distinction between past and future? Even more deeply than that, we walk around, we make our way around in the world with a very deep conviction that by acting now, we can affect the future but not the past. Why should that be true?
Although in the Soviet Union, allegedly, they would say that the future is known, but the past was always changing. Sorry, go on.
Why should something like that be true if the fundamental physical laws don't make any such distinction? Good. I think Boltzmann and Feynman were the first people to see clearly, look, this is apparently going to require something over and above the basic dynamical laws. This is going to require some kind of restriction on the physical initial conditions of the universe. Okay, and it becomes clear that at least one of the restrictions is the initial entropy of the universe is going to need to be very low, and so on. I try to make all this a little bit more explicit in my book to develop it a little further. And yeah, I gave it this name, the past hypothesis, but the idea has a long lineage before me. The past hypothesis is the name I give to whatever this restriction on initial conditions is going to need to be in order to explain all of these very pronounced kinds of time directedness in our everyday macroscopic experience of the world. What's exciting about this is that you have these very different kinds of directedness, thermodynamic kinds of directedness. Smoke spreads in a room, never collects back into a cigarette. Biological directedness, epistemic directedness, causal directedness. The exciting thing is, and once again, this is building on the groundwork laid by people like Boltzmann, The exciting thing is that there may be a single, fairly simple set of constraints on the initial conditions that you can impose that will get you at a stroke all of these different asymmetries, that they turn out all to be related to one another in a way that's not at all obvious when you begin to look at them. They look like very, very different things. What does the fact that smoke spreads in a room have to do with the fact that I can know more about the past than I know about the future, or that I can affect the past less than I can affect the future, or something like that? It turns out that you can make a plausible argument that all of them are pretty closely related, and that there may be fairly simple restrictions on the initial conditions of the world that'll get you something like that. Now, vis-a-vis contemporary cosmology, the business of characterizing what these initial conditions would be is going to depend a lot on how we manage eventually to put together quantum mechanics and gravitation, all kinds of stuff that are going to dramatically affect the very early parts of the universe. So what I would say at the present stage is if we're going to use the language of inflationary cosmology, at the end of inflation, okay, when fairly familiar sorts of physical laws are already in place and we think we know what the laws are that govern the evolution of the world from the end of inflation on, inflation had better leave us in some very low entropy state, okay, and a state with certain other characteristics that we can describe. What that means when you go back before the end of inflation or before the beginning of inflation, that's much more speculative, although presumably there's still going to be some sense in which the physical state of the world tends to wander from smaller regions of phase space into larger regions of the space of possible physical states. So there's going to be some story that's more or less like the story we have in statistical mechanics, but the precise contours of it, until we know much more about how to put gravitation together with quantum mechanics, we're not going to know about that. But there is a sort of general outline here. We have an idea, at least in the existing physical languages that we have, which become pretty secure by the end of the inflationary era, of what kind of conditions we're going to need to prevail there in order to underwrite the fact that even though the dynamical laws make no distinction at all between past and future, the world is full of these familiar kinds of distinctions.
Very good. So staying in the theme of cosmology, which butters the bread around the Keating household, one of the consequences, it seems, irreducible, at least according to Guth and Linde, the latter's been on the podcast, the former I'm trying to get on, is concomitant with inflation comes the multiverse. And I often hear it said that, in the multiverse, anything can happen, that will happen, that can happen, and even things that can't happen will happen. And even there may be different physical constants. There may be other laws of physics, fifth forces, ninth forces, infinite forces. And one thing I've been kind of curious, and you're the ideal person to ask it about, is why stop there? Why stop at just, quote unquote, the laws of physics, the constants of nature, the speed of light? Why not say, well, maybe modus tollens wouldn't hold in such parallel universes? Maybe modus tollens holds, but modus ponens doesn't hold. Or maybe the different, the distributed property of integers holds, but the associated. So can you tell me, are there any kind of conjectures about other forms of logic in other universes, or is this kind of a naive question?
Well, no, I don't think it's a naive question. I think it's a really interesting question. I'm not even sure that you need to go to other universes to begin to struggle with that. There is a very famous 20th century philosopher, maybe the most important 20th century philosopher, Quine, is famous for thinking in a very serious way that all of our knowledge is empirical, even our knowledge of logic, and so on. And there were people around the middle of the 20th century, there were serious philosophers who thought, many of these people had been students of Quine at Harvard, who thought that quantum mechanics, in particular phenomena like the double slit experiment, were examples of, suggested that we ought to give up on the universal validity of the distributive axiom. Okay, that if A is true and B and C are true, then it must be that if A is true and B or C is true, then it follows that either A and B is true or A and C is true. People thought that the double slit experiment put some pressure on a principle like that. That is, it would seem that that the interference pattern shows that it's true that the particle went through one slit or the other. Okay, excuse me. I won't reconstruct the whole argument here. But people thought, for example, that the two-slit experiment put pressure on a very important piece of classical logic.
So classical logic would then be different from quantum logic?
Right. Yeah, that's right. And it spurred this whole field of quantum logic, which people still work on.
Interesting.
I don't think anybody ended up thinking that this was a good solution to the conceptual problems of quantum mechanics for all sorts of reasons. But it did produce, this is a development that goes back to von Neumann. It did produce a whole field of logic with different logical axioms called quantum logic that logicians still work on to this day, just because it's formally interesting to them. So it is, you want to know my own view?
Yeah.
I start thinking, okay, what happens if I explore giving up the laws of logic? I don't know how to find my footing anymore. I don't know how to ask a question. If it's not the case that P and not P can't both be true, okay, then when I say P, I don't even know what I'm asserting, because I'm not asserting not P.
Right.
Okay, so I lose my footing very, very quickly when I try to think that logic itself is up for grabs. I don't know. Somebody says we reason from experimental results that classical logic is wrong. You want to ask them, how did you do that reasoning exactly? Weren't you using classical logic? What tools did you use to get that reasoning done? Okay.
Hey there, students of the impossible. Are you enjoying this deep dive into quantum mechanics, reality, the multiverse, physics and philosophy, and more? Well, there's more where this came from. In fact, when you join my Monday Magic mailing list, you'll receive exclusive content and fun facts, the latest science news, and highlights from your favorite podcast. You'll also get entered for giveaways to win things like my books and even meteorites like this one here, a real piece of 4 billion-year-old space schmutz. And in fact, you're guaranteed to win one if you have a .edu email address and you live in the United States. To enter to win, go to briankeating.com/list, or if you have a .edu email address, go to briankeating.com/edu. Now, back to our philosophizing.
I have a colleague at Columbia who I respect enormously, Justin Clark Doan in the philosophy department at Columbia, who doesn't think that's true at all, and who thinks that that logic may very well be up for grabs and so on. Certainly, it is. So, in response to your question, why hasn't anybody considered this? Well, they have.
They have.
Actually.
Okay. All right.
They have. People have taken it seriously. Like I say, I feel like I get a sense of vertigo when I try to think about this stuff. And like I told you, if somebody tells me a story, we did these experiments, reasoned about them, and concluded that some of the laws of logic must be false, my first question is, what was this story about reasoning about them?
Right, yeah.
What were you doing when you were doing that? Weren't you using classical logic? So I get lost. Maybe some other people don't get lost and will be able to see their way through this. But the idea that even logic may be up for grabs, may be an empirical science, is not, first of all, is not unknown in the history of, in the 20th century history of philosophy. And second of all, it's not unknown even in work on the foundations of quantum mechanics.
Interesting. So staying with philosophy and physics, question that's always sort of, maybe it's more of a statement. So I'll take my host liberty to run it by you and beg your indulgence to answer it perhaps. And that's, oftentimes we hear about, whether things are, Popperian or they're falsifiable or not as sort of the sine qua non of whether or not we're doing science.
Right.
Of course, there's trivial objections to that. I can make a horoscope prediction, which also will be falsified. Therefore, it's falsifiable. Therefore, astrology is science. I think it's kind of ludicrous. And people have updated this, got Thomas Keyes, the theoretical virtues. But my question is more of a sort that, I believe that it's often said that the social sciences that are some of our colleagues practice and traffic in, they're guilty of having physics envy, that they wish that they were rigorous and so forth. But at a level that I think is not really appreciated, that I think physicists have mathematic envy or mathematician envy, because at least in mathematics, there's Gödel's incompleteness theorem. You can know which axioms are not derivable or inconsistent with the propositions or postulates of that theory, right? But physics has no such thing. So I think a lot of times Popper sort of substitutes for Gödel, but they're very different in terms of a logical sort of self-consistency and completeness. Is there something that, if you were, sort of to say has supplanted Popper in terms of a working practical definition that I can say phrenology and dream interpretations, as Popper was railing against in the early 1900s,
right,
are not science, are not part of the program of empirical science? Is there any rubric I can use?
I think that's hard. I think that's hard to answer in any simple way. And indeed, Popper is somebody who very much appealed to working scientists. Working scientists really felt that Popper got something about what they were doing that other philosophers hadn't gotten. He's much less of a revered figure in philosophy.
Sure.
Here are some of the reasons. The problem that Popper was addressing, the problem of induction, okay? How do we know? We do a small, this funny thing happens in physics. We do a very small number of actual experiments and observations, and the next thing you know, we're declaring with high confidence that a certain law, which of course has an infinite number of consequences, is true.
True.
Okay? And moreover, we're not crazy to do that. Okay? We do that, and we've had good results from doing that. And you say, what the hell can be going on? How does this work? How do we confirm, okay, from a small number of experiments that a general statement that applies to every location in the universe, places where we've never been and never will be, is likely to be true? Okay, good. Popper is famous for saying, no, you can't, there is no grounds for believing anything like that is true. All we get from the progress of science is a larger and larger collection of theories which we now know to be false. Okay? And that's what scientific progress is about. Now, immediately you have a bunch of questions. Well, really? If that's the case, why should I be confident about getting on airplanes and so on and so forth?
Putting my bank account
Popper was
online.
very adamant about this. The difference between scientific speculation and other kinds of speculation is precisely this falsifiability. And I think that lots of working scientists saw in this a heroic and attractive image of themselves, okay? That is, Popper said, and this is a nice catchphrase, you want to know what the difference is between science and other branches of human speculation, theology, philosophy, religion, so on and so forth. The difference is that in all these other activities, people are working as hard as they can to prove that their favorite theory is true. What scientists do is work as hard as they can to prove that their favorite theory is false. Okay? And this is a real devotion to truth. Okay? And you tell these stories about, about people schlepping out into the jungle and catching malaria in order to witness this eclipse where they could confirm, where they could test general relativity. Why are these people catching malaria and so on? They're doing it for the opportunity to prove their favorite theory false. Okay? This struck people as a real heroic devotion to truth. But look, I get it. I see why this is appealing. You begin to scrutinize this, it's not so easy to make sense of it. For example, something that was pointed out long before Popper, especially by a 19th century French figure named Duhem, D-U-H-E-M, who said, look, there can't be such a thing as simply refuting a theory by an observation that doesn't make all sorts of assumptions that other theories are true. Okay? I say the results of this bubble chamber test refute this theory of the weak interactions. Okay? You say, but, well, in order to assert that, aren't you making all sorts of assumptions that your theory of the operations of the bubble chamber are true? That this track in the bubble chamber indicates what you think it indicates? Or on an even more fundamental level, you say, I make this observation, this shows that theory X is false. You say, but aren't you assuming that certain other theories, like theories of the way your eyes work and so on, are true here? Okay? So Popper's big idea was that there could be falsification without confirmation. Okay, falsification could stand on its own. Okay,
as a teleological.
Right. To confirm that a theory is true, you would have to make an infinite number of observations. But to confirm that it's false, you just need one. Okay? And falsification can stand on its own. And lots of people pointed out, and Popper wasn't very good at listening to this or responding to it, saying, well, I don't really get that. These so-called falsifying experiments, don't they rely on assumptions that certain other theories are true? And if you weren't assuming that this theory of the way your eyes work are true, then your observation will not have falsified theory X. Okay? So the idea that falsification could stand all on its own seems, when you begin to scrutinize it, not correct. Okay? So Popper wanted to find a way to talk about scientific progress that did away with confirmation. Nothing ever gets confirmed. Things just get falsified. Okay? People came back and said, if nothing is confirmed, nothing ever gets falsified. Okay.
The confirmation can come in the form of, more and more refined observations. The perihelion advance of Mercury is a minute effect, good. Right? It's a minute effect, so Newton is correct. Yeah,
that's fine. Popper wanted to do away with all that. Popper wanted to rely only on falsification. Okay, this was really crucial for him. And a lot of people rightly said, I'm sorry, if there's no confirmation, there's no falsification. Okay. So Popper is not as widely respected in philosophy as I think he still is in lots of parts of science. As to your bigger question, and this makes it tough, a clear demarcation between scientific work and other kinds of work, I think is really hard to make. It's obvious that there's a really important sense in which the final arbiter of our scientific thinking is empirical. Okay, that's a really but exactly how that enters in and exactly what other criteria besides empirical ones we use in choosing which theory to believe, this is a very hard problem. We clearly have a fairly reliable sense of it as we go along in the scientific project, but it's clearly also something that's evolving, and I think it's a very hard thing to make a clean statement about.
So we have about 15 minutes left before we have to leave for your colloquium, which you're graciously giving here at UCSD. And for the benefit of those people who don't live in our fair city, the America's finest city, would you mind kind of capitulating what the talk is going to cover? Physics and narrative. So usually, David, I don't like it when I'm asked to be on a podcast and the host will say, can you describe your book and basically make it like a short form summary, so Blinkist, so we don't have to buy it. No, I'm not going to ask you to do that. But for colloquium, you're not losing any royalties. So could you go into as much detail as you feel comfortable? Sure. And then we could turn to about 50 questions from the audience, but we'll have to be selective.
So very briefly, there's a very simple thought experiment you can do that suggests that in theories which are both quantum mechanical and relativistic, you can't say everything there is to say about the history of the world by saying this was the state at this time and that's the state. That is, you have a one parameter family of states. You have an assignment of a state to every time in some particular Lorentz frame of reference. And then you naively think, once you have that assignment in one frame of reference, you can simply do a Lorentz transformation and get it in another frame of reference. That's true in non-relativistic theories. That's true in things like Maxwellian electrodynamics. That's true in non-relativistic quantum mechanics. The upshot of this talk is that it's not true in relativistic quantum mechanics.
Interesting.
And, this is another case of having to relinquish a very deeply intuitively entrenched idea about what the world must be like. This is something which we were not forced to give up by relativity, and we're not forced to give up by quantum mechanics, but we are forced to give it up by the combination of the two. So that's what my talk is going to be.
And too bad for those of you out there, you're going to miss out on the cookies and coffee that we provide, the finest the state of California will supply. Okay, we have a bunch of questions, 63 questions from the audience. We'll have to do these rapid fire. We're not going to take all of them. Start with one, and a reminder, you can always ask questions of my esteemed guest. I always post on Twitter or Instagram even, or Threads, or no, I'm not on Mastodon. Any of these places, but especially on the YouTube channel, Dr. Brian Keating. So if you're listening to this, go over there, make sure you subscribe so you can ask questions. And I solicit them there, and also via my email mailing list, the Monday Magic Musings that I send out each week. And that is also going to entitle you to a free meteorite. David gets one of these. This is a meteorite. It's 4 billion year old piece of space schmutz. So hold that up for the camera. There you go. That's a part of your gift for coming here.
Thank you. That's a lovely gift.
Guaranteed to win one of those if you have a .edu email address and you sign up for the mailing list. The link is right here, briankeating.com. And otherwise, I do give them away to people that aren't privileged to be at one of our nation's finest research universities. David, first question comes from Walter Hassel. Very excited for this. I'd love to hear his answer to the question. If it were discovered that one of our best attested scientific theories was completely cognitively unstable due to an abundance of Boltzmann brains or observers, such as the core theory of physics, John Carroll's nomenclature, what would we make of that? What should we do with cognitively unstable, or maybe it means untestable, but unstable?
No, I think he means unstable.
So what does that mean?
That's a term of mine.
Okay, great.
I take myself to have good reasons for believing that I'm a Boltzmann brain. Why? I have all these experiments that I did that convince me that the laws of physics have a certain structure, and those laws suggest that the vast majority of brains that will ever exist in physical states like mine are brains that recently just fluctuated out of dust clouds and so on. That's why I believe I'm a Boltzmann brain. This position is something I characterize as cognitively unstable in the following sense. You say to this guy, but wait a minute. You say that your knowledge of the laws of physics, which you obtained by doing experiments, suggests, if you do out the calculations, that you're most likely a Boltzmann brain. Right. But if you're a Boltzmann brain, that means you never actually did do these experiments. Your memories of these experiments having been done and how they came out are all false. They were created by one of these fluctuations. So you can't. It can't be the case that you come to me and say, because of my study, my empirical and theoretical study of physics, I've become convinced that it's very likely that I'm a Boltzmann brain. Because once again, you're just saying that denies that these empirical and theoretical studies of physics ever took place. Okay, so this is a position that I characterize as cognitively unstable. Okay. You can't, in a stable way, come and announce that your studies of physics, your investigation of physics, suggests that you're a Boltzmann brain, suggests that you never did these investigations in the first place. Good. That's what I call a cognitively unstable theory. And if, I don't know what, for the reasons I just explained, I don't think we could have good evidence that that the true theory of the world is one that produces this kind of cognitive instability. Okay, if it looks like our true theory of the world is producing, is putting us in a position like that, that's a bad situation. Okay, we've got to look for some other kind of theory. I think it has to be the case. I think it ought to be a requirement on an acceptable physical theory. Not just that it's empirically adequate, okay, but that it describes the kind of world in which there could be observers like us who come to have good reasons to believe that these are the laws of physics, okay? Cognitively unstable theories don't allow you to do that. Right. And it seems to me like it ought to be a basic requirement of an acceptable theory of physics, just like empirical adequacy is a basic requirement, that the physics ought to be able to describe how beings like us could have gotten into the cognitive position that we find ourselves in.
This comes from someone named Doozy Titter, which I actually considered as one of my kids' names. As an expert in the foundations of quantum mechanics, you may have seen the recent publication of Oppenheim's Post-Quantum Classical Gravity, which assumes a stochastic interpretation of quantum mechanics. I've heard vague things about this, but if it was true, proposed experiments indicate this is a viable theory. What does that mean for quantum mechanics?
That's a really good question, and I just have to confess that I haven't studied this theory.
Me neither, yeah. I might have him on the show.
And I thank you for alerting me to it, and I should study it.
Great. And the students out there, make note, that's how you're supposed to answer a question, not say some blue sky stuff. Okay, Robinson9714 asks, how can thermodynamics determine the arrow of time if thermodynamics is not the identity of time? Because the classical Newtonian Einstein time dimension is ? I guess, yeah. How can thermodynamics determine the arrow of time?
Well, let's see. I'm not sure I understand the question.
Me neither.
We observe the following: the direction in which the entropies of various different systems rise, bowls of soup, puffs of smoke, so on and so forth. Their entropies all rise in the same temporal direction. Okay. Moreover, the direction in which they get lower is the direction that we find we can remember. The direction in which they get higher is the direction we find we can influence by acting now. So there are all of these coincidences. I don't believe, if the question is, how can this explain why time itself, as a part of the fundamental metaphysical structure of the world, has a direction, I don't think it does. Okay, I'm a firm believer in the sort of block picture of the universe. There's just this big four-dimensional thing with a distribution of physical properties over it. It turns out that the distribution of physical properties is very asymmetric in one direction of time as opposed to the other direction of time. We want to know why the distribution is like that. And when you put it that way, it becomes useful, it becomes natural to look for an explanation in terms of constraints on the conditions on one end.
Okay, this is a provocative one. Feel free to not take it, but Punch McLightning asked the question, wasn't this guy in The Secret one of the most unscientific BS documentaries ever? Ask him why I should trust anything from him after being part of such pseudoscience BS. So you were not in The Secret?
Good. I wasn't in The Secret. I was in What the Bleep Do We Know? And anybody who looks at the history of that will find that I thought I was very badly misrepresented in the film. So there was a lot of press about this at the time. This was a long time ago. But look, you should make decisions about who to believe by who seems to be talking sensibly and clearly and understandably. But you're absolutely right. I was incredibly stupid to allow myself to be interviewed by these people before looking more carefully into who they were and so on and so forth. These people, I'm just repeating stuff that came out in the press at the time, but these people interviewed me for about 4 hours, edited it wildly, and I ended up being in the film for a total of maybe 90 seconds or 2 minutes or something like that. And they had edited me in such a way as to make it appear that I was saying exactly the opposite of what I was saying. So, learn my lesson. This was really stupid on my part. I agree with that 100%. But it's not as if I endorse the claims that this film made. I made it very, very clear later on that I don't.
Absolutely, great. Okay, well, to as a solve on your ego, Space in Your Face says great choice of guest. Time as Havadar says I love him. Okay, time as he's taken, and you probably aren't as good an artist as his wife is. Okay, okay. This one has to do with the multiverse. Paul de Souza. A curious layperson. How does David see the idea of a multiverse for which we lack experimental evidence? And how does that stand against the intelligent creation design proposed by some as a consequence of the fine-tuning problem? And we've had on Paul Davies, who said things that, and I've agreed with this, and I made a video about this. What's a greater leap of faith, God or the multiverse? What are your positions on the multiverse?
Well, first of all, I don't think it's quite fair to say that the multiverse, specifically as it comes up in the context of inflation and stuff like that, is something for which we have no empirical evidence. That doesn't seem right. Maybe it's fair to say that our empirical evidence is indirect, okay? But the situation, as I understand it, is this. We're initially in the business of trying to explain the universe we see, okay? It turns out, at least, this is our best guess at the moment, that the best scientific explanation we can think of for the phenomena that we actually see is a theory that, if you take it seriously, entails that there are other universes as well. Okay. So what are our reasons for believing in this theory in the first place? They're empirical reasons. Okay. What are our reasons for believing in the existence of these other universes? Well, the theory that's best empirically supported by what we do actually see entails the consequence that there are these other universes. In a case like that, I would say our reasons for believing in these other universes are empirical reasons. It's not because we directly see them, but empirical data forces us onto a theory that has the logical consequence that there are these other universes.
But it's contingent upon inflation being...
Yeah. No. Inflation being the best, maybe it's not. But just in the abstract case, somebody says, how could anybody take seriously a theory that entails there are other universes, since we can't see those other universes? The answer is that theory also entails things about our universe. That's why we adopted it in the first place. And if it turns out, this is a big if with inflation, but if it turns out that this is the only reasonable theory that can explain what we do actually see, and if this theory turns out to entail that there are other universes, in that case, I think the right way to describe the situation is that we do have empirical evidence for the existence of other universes.
Okay. Or that at least it is in the situation that it could be proven or confirmed, but not falsified necessarily, because we could bump into another universe. There could be, a billboard that says, "I am not in your universe."
No. That could be right.
Right,
but it's also just right. It's like saying, I don't see how it's so different from, you talk about the effects of gravitation on medium-sized bodies in galaxies that we're never going to be able to visit. Right. We say we're confident that even in those galaxies, objects fall towards gravitating centers in such and such a way. You say, why do you believe that? You can't see it. I say, here's why I believe it. The stuff I can see is best explained by this kind of theory. This kind of theory, once I adopt it, entails things about what's going on in these other galaxies. That's so right. I believe those claims about what's going on in those other galaxies.
That's right. Okay, last question. This one comes from my friend, Professor Luke Barnes at Western Sydney University.
I know Luke.
Yeah, he's a great friend of the show. He's been on multiple times. He makes a controversial claim. He says, if Bohmian mechanics had been proposed first, no one would have proposed the Copenhagen interpretation.
Right.
Your thoughts, sir?
I think that's absolutely right. I think, somebody had discovered Bohmian mechanics, and you imagine Bohr then walking into a room and saying, no, I've got a whole new view, okay? It's much more elegant. It respects the symmetry between position space and momentum space, blah, blah, blah. The only little catch is that you have to give up on the idea that there's a real external world out there. Okay, I think he would have been laughed out of the room.
Right.
Sure.
Yeah. Maybe one last question from Ozymandias _. Twitter. When will philosophy get its balls back and stop letting string theorists and other theoreticians propose horribly thought out metaphysical theories for their scientific systems? That's part one. I'm not going to ask part two. It's too complicated for me to understand. Philosophy, get its balls back. People, our mutual friend, Lawrence Krauss, of course, always loves to assail philosophers, including you truly.
Right.
In your scathing.
If you bring up, say, this controversy with Krauss, it sounds to me like philosophers have gotten their balls back, and
yes.
and they are criticizing not well thought through claims of physicists. Yeah.
Okay. One more question. How come you never, or two more questions. What do you think about pineapple on pizza from Jay Brown?
I hate it.
Hate it. Good. Check. And someone also asked, well, you never mentioned the marital status of number 5. How is it doing?
So this must be somebody who's been in a class of mine.
Yes.
This is often the way I try to describe the sort of conventional understanding of superpositions in quantum mechanics. If a particle is in a superposition of being located here and here, it's not that it's in one place or the other. It's not that it's in both places. It's not that it's in neither place. It's some other state of being such that there's some sense in which it doesn't even make sense to ask questions about the location of the particle. That is, asking questions about the location of the particle would be like asking questions about the marital status of the number 5.
Very good. So, David, we have a tradition at the end of each conversation. I love to ask existential questions. We don't have that much time. I want to give you some time to take a nap before your colloquium.
That'd be good.
I don't know if I'll have time. You're on Eastern time. And that usually there are different forms of questions or comments or statements proposed by Arthur C. Clarke. My mailing list comes from the name Magic Monday mailing list comes from the fact that Arthur C. Clarke said any sufficiently advanced technology is indistinguishable from magic. You may not know this, but the word podcast comes from Arthur C. Clarke indirectly.
Really?
Yep. In fact, in 2001, A Space Odyssey, Dave is asking Hal to open the pod bay doors. Pod bay is controlled by Hal, and it's sort of reminiscent for Steve Jobs and his engineers at Apple that they would call the iPod after the pod.
I once had dinner with Arthur C. Clarke.
No way.
Yeah.
What was that like?
It was great.
Where
it
were
was
you?
really, really fun.
Sri Lanka?
He was an old friend of an uncle of mine.
Wow.
And this was, I guess, not too long. So I was young then. Yeah. This was not too long after 2001 came
68
out.
68 or 67.
And so it must have been sometime in the early 70s, something like that. My uncle said, my old friend Arthur C. Clarke is in from Sri Lanka.
Wow.
I'm having dinner with him. You want to come along? And so I did. It was lots and lots of fun.
Wow, that's incredible. Yeah, I never got to meet him, but I've had a lot to do with him over the years as the co-associate director of the R.C. Clarke Center for Human Imagination. One of the things he said famously, many things, including the name of this podcast, comes from a statement that the only way to determine the limits of the possible are to go beyond them into the impossible. And then the thing I like to drop on my department chair from time to time when he asked me to do more teaching is, he used to say, for every expert, there's an equal and opposite expert. And then lastly, he said, and I'm going to conclude the podcast with this, he said that when an elderly, I'm not calling you elderly, but I am calling you distinguished, scientist says something is possible, he or she is very much certainly right. But when he or she says something is impossible, they are most certainly apt to be wrong. I want to ask you in the context of, what have you been wrong about? What have you changed your mind about?
Oh, gee, lots. I've been wrong about tons of things. I've changed my mind about tons of things. I can remember when, under the influence of a false popular image of Einstein, I thought that what was puzzling about quantum mechanics was that it was chancy. First of all, it turns out this is a mischaracterization of Einstein. This business about playing dice with the universe, which is very often quoted, is quoted out of context. I feel like one of the things I've learned over a career of thinking about the foundations of quantum mechanics is that's not the problem. It's perfectly okay and it's perfectly conceivable that nature turns out to be fundamentally chancy at bottom. What's not conceivable is that it turns out, going back to our earlier discussion, to be what's hard to imagine is a position like Bohr's, where you say, look, we did these experiments. We noted where the positions on the pointers ended up at the ends of these experiments. And as a result of this investigation, we have concluded that there is no real external world. Sort of say, how did that work? I must have dozed off there for a minute, okay? How did you get from the positions of certain pointers to the claim that there can't be a real external world, okay, in the old-fashioned philosophical sense? This is what I've gradually realized is what's really at stake in the foundations of quantum mechanics. I'm wrong about almost everything. This is what gives me the opportunity to keep thinking and writing, more books to correct everything I said wrong in previous books.
Update your priors. That's all it is.
The business of being wrong is what intellectual life is about. I take it.
Wonderful. Well, if we had another, 20 hours to converse, I don't think I'd run out of questions for you. My audience is clearly in love with your brain, as are millions of people around the world. David Z. Albert, exceptional thinker, scholar, what it means to be a scholar. You heard, I have many young people that listen to this podcast, and many of them are interested in science. And you heard today an example, kind of a masterclass in what it's like to be a scientist at a very high level, to admit when you're wrong, to understand when you're right, and to be bold and go into that unknown and into the impossible, as David clearly has. David Albert, thank you so much for coming here to San Diego. And this has been a delight.
Really nice.
Thank you.
Thank you.
Hey, if you made it all the way to the end, feel free to watch this episode with David's friend, Lawrence Krauss, from our live interview back at the San Diego Air and Space Museum. And click here for a playlist of the best episodes from the past few weeks.